So we now look at the equations, radical equations. Solve for x. Examples. Question 1. So these are the easiest questions to solve. One plus the root of x minus 4 is equal to 3. First thing is we take this one the other side. So we have root of x minus 4 is equal to 3 minus 1. That's the solution. So that we get root of x minus 4 is equal to 2. Then this part will be squared. Also this part will be squared. So we'll get x minus 4 is equal to 4. Take 4 the other side. We'll get x is equal to 4 plus 4, which is equal to 8. Now, when you get these values of x, you must be quick to go back and confirm that that is true. So 1 plus, so test 1 plus the root of 8 minus 4, that is 1 plus the root of 4, which is 1 plus 2, which is equal to 3, our right hand side. So x is equal to 8. Confirmed. Two, the root of x minus 2 minus the root of x plus 5 is equal to 1. First thing, take one of these guys the other side. So that you remain with 1 is equal to 1 plus the root of x plus 5. Then now that's when you square and square. So on the left, it will be x minus 2. On the right, it will be 1 plus this guy multiplied by itself. So that we still have x minus 2. Then 1 times 1 is 1. Plus 1 times the root of x plus 5. Again, x plus 5. And then plus x plus 5. So I'm sure this x and that x will cancel. So now we'll have negative 2. 1 plus 5, that is 6. So negative 2 minus 6 should be the same as 2 root of x plus 5. So we've added, because there are 2 of them, we have 1 here and 1 there. So we put them together, so there will be 2 of those roots. This is negative 8 is equal to 2 root x plus 5. So to avoid confusion, we can divide by 2, divide by 2. So we'll get negative 4 is equal to the root of x plus 5. Normally, when the root is negative, is negative like that. When the root is greater to a negative number like that, when the root is positive, it's a signal that there might be no solution here. So we'll try, let's square this and square this. So we'll have 16 is equal to x plus 5. Then solve for x. So it will be 16 minus 5. So x is equal to 11. So let's take it there and see if things will come out. So root of 11, so test. Root of 11 minus 2 minus Root of 11 plus 5. This is 11 minus 2, that is 9, minus 16. This is 3 minus 4, which is equal to -1. But this is not equal to 1. Therefore, the solution set here is empty. So there are no values of x for which that thing gives us a 1. So this is what we counted in that example where we're trying to check if there was to be an x-intercept. So you saw that it had a negative, then we squared the negative. So it could not come out because that nature, because the root by nature, the root of 16 is 4. And not plus or minus 4. It's only plus or minus 4 if you're having an equation of this nature is equal to 0. We are saying what values of x can give you 0 there. It's possible that x can be positive 4 when squared, we'll get 16 to get 0. X can be negative 4 when squared, we'll get 16 to give us 0. But not that the root of 16 is 4, no. I mean negative 4, no. Another example to see up the radical equations will be the root of 1 plus the root of x is equal to the root of x plus 1. So let's see if that is possible. First thing, square, square. So we have 1 plus the root of x is equal to x plus 1. So the ones will cancel, will remain with root x is equal to x. Square, square. So we have x is equal to x squared, giving us x squared minus x is equal to 0. Factor out x, remain with x minus 1. So never divide a variable. Please never divide a variable. Okay, so just factor it out so that you get x is equal to 0 or x is equal to 1. Then get these values, go and test now. So when x is 0, we'll have the root of 1. So test the root of 1 plus root 0. This is just the root of 1, which is 1. The right hand side will have 0 plus 1, which is just the root of 1, which is 1. So these two are equal. So x is equal to 0. Let's check the other one. When x is 1, we'll have the root of 1 plus root 1. This is the same as root 1 plus 1, which is root 2. On the right hand side, 1 plus 1, that is root 2. So also x is equal to 1. These are our solutions. The danger of dividing is the variable is if you divide, let's say you do this, and then divide by x, divide by x, divide by x, you get x minus 1 is equal to 0. So we just have x is equal to 1. Forgetting about the other one, when we are supposed to also have x is equal to 0. That's why we never divide the variable. Or we should say never divide by the variable. Okay, yeah. Never divide by the variable. Okay. So I think this is enough for radicals. You're able to solve any kind of radicals. So you should also know that it's possible to have radicals of this nature is equal to 2x squared plus 6x plus 4. So you find yourself in this situation, you square, you remain with x squared plus 3x plus 2 is equal to 2x squared plus 6x plus 4. Then take the left one on the other side so that you have 2x squared minus x squared plus 6x minus 3x plus 4 minus 2 is equal to 0. And get x squared plus 3x plus 2 is 0. Get the values of x. That would be x squared plus x plus 2x plus 2 is 0. So x plus 1, x plus 1. So we have x plus 1 and x plus 2 giving us 0. X is -1 or x is -2. So if you test, they will satisfy those equations because they're the values of x that we have obtained here. If you try to test, they will both satisfy the equations. So no matter how complicated the things inside are, your task is to make sure that you get rid of all the roots by squaring. You can square as many times as possible until you no longer have a square root, until you have the actual values of x. That is what we do, unless we have questions. Okay, no questions. So have we looked at the absolute value functions?
No, sir.
Not yet. Okay, so now we can start absolute value functions. We'll also start with the graphs. So these are in two types. We only have two families. One, f of x is equal to a plus bx plus c. And the second family is f of x is equal to a minus bx plus c. We don't care what the b is, whether negative or positive, we only have two families. So the first family, the graphs face up. Second family, the graphs face down. It does not mean that they're always be on the x-axis. They can be anywhere, but these will be the shapes. And they'll be very easy to sketch now that we have done radicals. At least we have an idea of having sketches of families. Examples, sketch 1, f of x is the modulus of x. Now, one thing we must know is that the modulus of x is defined as x if x is greater or equal to 0. And it is negative x if x is less than 0. What does this mean? If you have 2, the definition is just 2. If you have negative 3, because negative 3 is less than 0, the definition will be negative multiplied by negative 3, so that we obtain a 3. The purpose of the modulus is to keep a number positive. So if a number is negative, it must be made positive. That means that we can as well say this guy is the same as the square root of x squared. What do we mean? If you give me 2, it's the same as the square root of 2 squared. This is the square root of 4, which is 2. So it doesn't make sense if it is already positive. Now let's see the square root of, the absolute of negative 3. This will be the square root of negative 3 squared, so that we get a square root of 9, which is 3. The idea was to make this negative 3 positive, and we have made it positive. So
yes. I'm not really clear. Can you please repeat?
Okay. So in trying to make a number positive, the modulus, these guys were specifically introduced to make numbers positive. That's the role of the modulus. So if they give us the modulus of x, what we will do to this x is that if it is already positive, we'll leave it as x. That is, if it is already positive or 0. But if it is a negative number, we'll multiply it by another negative so that we make it positive. That's why now we said, could there be another way? Yes. We can as well make a number positive by squaring that number first and then get its square root. For example, if we are given 2 in the modulus, because it's already positive, there's no need of modulus. But if it was negative 3 and don't want to use the modulus, we want to use another definition. Suppose we use this one here. Because negative 3 is less than 0, because x is less than 0, negative 3 is less than 0. So we multiply it by another negative so that it becomes positive. Or we would have decided to take this in the square root. We square it, it will become 9. Then get the square root, it will be 3. We have achieved our mission to make it positive. So now the question was asking us to sketch. So I want to sketch the modulus of x. So we sketch the modulus of x. To sketch the modulus of x, first method, you go straight to f of x is equal to the modulus of x. Get the inside and equate it to 0. Then take it in the function f of 0. The modulus of 0 is 0. So we have a starting point 0, 0. From the two families, we said the family on top is facing up. The family down, facing down. Now in this case, we are in the family on top where the outside is positive. So start from there. If we don't know and don't want to memorize, pick a number bigger than 0. Pick a number bigger than that value. Let's say 1. What is f of 1? F of 1 is the modulus of 1, which is 1. So we have 1. So we have 1, 1. Pick a number less than 0. F of -1. The modulus of -1 is just 1. So we have -1, 1. So we know this is going up. This is going down. So we have sketched our function. Or second method, use these functions. So for x greater or equal to 0, you are using the top function. Meaning when x is 0, you substitute in the top function, which includes 0 here. So you get 0. So you have 0, 0. When x is 1 bigger than 0, you use the same function on top. F of 1 is x, meaning it is 1. So you have 1, 1, and draw a line this side. Then you go to the other domain. X is less than 0. So when f of x, let's say we use -2. -2 is less than 0, so we must get -2, which is +2. So we have 2, 2, a point somewhere there, meaning that the graph is coming this way. So we have again sketched the graph, the same graph, using a different method. So now I want us to capitalize on this one. It looks easy. So let's see. Example 2, f of x is equal to -2 plus the modulus of 3x plus 1. First thing, you get the inside of the modulus equal to 0. So for x, divide by 3, divide by 3, x is equal to -1/3. This number here, we get as it is, take it in f. So what is f of -1/3? That is -2 plus 3, -1/3 plus 1. So that we get -2 plus -1 plus 1, which is -2 plus 0, which is -2. So we have a point, -1/3, -2. So we can sketch. The starting point is known, -1/3, -2. So this is our starting point. So let's pick a number bigger than -1/3. Now, if we have a negative number, to your right, you pick 0, so that you have an opportunity to also know the y-intercept. That is -2 plus 3, 0 plus 1, giving us -2 plus 1, that is -2 plus 1, which is -1. So we get 0, -1, meaning that it will cross there. So this is -1. On the left, obviously because it has gone up, this side it will also go up. We have a task now to know the x-intercept. So we have an opportunity to solve these also. We know that the x-intercept is always when f of x is 0. So equate the whole function to 0. So take this guy the other side. So how the modulus of 3x plus 1 is equal to +2. Then how do we define this guy? We've said it's defined in 2 pieces. So we use those pieces. So 3x, it is 3x plus 1 is equal to 2, or negative 3x plus 1 is equal to 2. So for this condition, we require that 3x plus 1 be greater or equal to 0. For the other condition, 3x plus 1 be less than 0. But because we're just solving for the values of x, for the intercepts, we'll concentrate less on this. So don't pay much attention there. Just mention them and leave them there. And then deal with 3x plus 1 is equal to 2, giving us 3x is equal to 2 minus 1. That is 3x is equal to 1. Divide by 3. Divide by 3. So x is 1 over 3. So this is 1 over 3. And then negative 3x plus 1 is equal to 2. That is negative 3x minus 1 is equal to 2. So negative 3x is equal to 2 plus 1. That will be 3. Divide by negative 3. Divide by negative 3. This means that x is equal to negative 1. So this is negative 1. That's how you get to know there was intercepts there. So this is a detailed graph. That was example 2. Example 3, f of x is equal to the modulus of x minus 1 plus the modulus of x plus 2. Now we have 2 of them. So what we do is we first get the first piece, redefine it, x minus 1 for x minus 1 greater or equal to 0, negative x minus 1 for x minus 1 less than 0. Notice that what we put here is the same. Where we change the sign is on this part here. So don't confuse the two, that you end up changing the sign of this piece also. No, you don't get to do that. So then we simplify. This is the same as x minus 1 when x is greater or equal to 1, and negative x plus 1 when x is less than 1. We also get the modulus of x plus 2, have it redefined as x plus 2 if x plus 2 is greater or equal to 0, as negative x plus 2 if x plus 2 is less than 0. This means that it will be x plus 2 if x is greater or equal to negative 2. It will be negative x minus 2 if x is less than negative 2. So we have 2 numbers, 1 and negative 2. So we form a table for these 2 numbers. Draw lines there, lines here. Demarcate again there, demarcate again there. Close, close, close here. Then get the modulus of x minus 1. Give it its box. Get the modulus of x plus 2 in its box. And then you have the whole f of x in the last box. So this interval here is for x less than -2. The middle interval is for -2 less or equal to x, which is less than 1. This interval is x greater or equal to 1. So we go to the modulus of x minus 1. The modulus of x minus 1 is defined as x minus 1 when x is greater than 1. So in the interval where x is greater than 1, this piece is defined as x minus 1. In the interval where x is less than 1, in this interval x is less than 1, it is defined as -x plus 1. Now when x is less than 2, automatically it is less than 1. So it is still defined as -x plus 1. We go to x plus 2. In the interval where x is less than -2, it is defined as -x minus 2. In the interval where x is greater or equal to -2, it is defined as x plus 2. Now when x is greater or equal to 1, automatically it is greater than -2. So we have x plus 2. And then add the intervals per, add the functions per interval. So -x plus -x, we get -2x. +1 minus 2, we get -1. -x plus x, we get 0. 1 plus 2, we get 3. And x plus x, we get 2x. -1 plus 2, we get 1. And then sketch now. What we are sketching are the three functions. So the easiest one is x is equal to 3 from -2 to 1. And 1 is not included, but -2 is included. It's just a straight line 3 throughout that interval there. Then when x is bigger than 1, you are using this one. So you start by substituting 1 in there. You get 2 plus 1, which is 3, mean that you close this piece here. Then substitute one number and see if you go up or down. So 2 plus 1, that is 4 plus 1, which is 5, mean that we are going up. Then come to the left, substitute -3 in this function here and see where you are going. -2, -3, minus 1, that is +6, minus 1, which is 5. So we're also going up. That is the sketch of f of x. So this is f of x, the whole sketch here.
So I just blew my mind here, like.
Sir, could you repeat up just after you finish drawing the table there?
Sir, this one was the 1% students who got it.
Yes, this is the kind.
Yes, just after you finish drawing the tables, and it's not, I don't know.
Look, between -2 and 1, in this whole interval, the function is 3. So it's a constant function. So it's just a line, y is equal to 3 throughout these numbers for x. That's why we have that line there. So it's including -2, but it was excluding 1. So we are done drawing that one, just a straight line. Then we are remaining with this function on the right when x is greater or equal to 1. So if you get 1, substitute here. We got 1, substituted, and got 3. Then we went there and checked there was a hole. So we closed it because of that 3. Then pick any big number because x must be greater than 1. So pick a number greater than 1, let's say 2. Substitute there, you get 5. This 5 is just telling you that your graph will go up and not down. If we got 2, which is less than 3, the graph would have come down. Now I got 5, which is bigger than 3, the graph went up. So we are done on the right. You go to your left, you find this function here. for values of x that are less than -2. So you come substitute -3, which is less than -2. Substitute in there, we got 5, bigger than 3, meaning the graph is going up. Then that's all.
All right, so okay.
Yeah, where is 1 included? 1 is only included to this part, not
1 is only included
1 is
to which part? This part here.
also not this part here.
Yeah, not
The-
the other part.
Okay.
So I mean, I was just, I don't know if we can just, like, where you just started drawing like a table there, like where you got these values, okay, like it's buzzing me.
Well, now you understand how these numbers are coming up.
Yes, I understand that.
So you get that the smallest of these two. So -2, we place it here. 1, we place it there. So we are saying this interval here are for the numbers between -2 and 1. After, they are for numbers greater or equal to 1. Before, for -2 or less. Then now you go back to your functions. What is this guy when x is bigger than 1? It is x minus 1. So we put x minus 1 here. What is this guy when x is less than 1? Have I saved? Okay, yes. So it'll be cutting anytime soon. So when x is -1, so when it cuts, we rejoin. We have more work to do. When x is -1, we'll get x minus 1 for x less than 1. We are getting -x plus 1. So this whole interval here is less than 1. X is less than 1, x is less than -2. Any number less than -2 automatically is less than 1. That's why the same function has appeared here and there. Then you got the down number, -2. The other function, this guy, for x less than -2, it is -x minus 2. So x less than 2, it is